Good morning, everyone. Thanks for the kind introduction. I'm Houxiang from UIUC, and I'm excited to present our work, Para-ksm, Parallelized Memory Deduplication with Data Streaming Accelerator. This work is a collaboration between UIUC, Digest, and Yonsei University. The codes are also open sourced at GitHub. So let's get started with some background about memory deduplication. The idea is to consolidate pages with the same content so that we can save the physical memory space. For example, with the limited memory capacity, now you can host more virtual machines or containers in the cloud. So in the Linux kernel, this is handled by Kernel Same-page Merging, or KSM. While KSM is effective in the saving memory, it introduces notable CPU overhead. For example, in this figure, we can see that when KSM is running with Redis application for database, we can see it takes up to 60% CPU utilization due to the massive execution of the operations like memory comparison or checksum calculation. So the key question is, can we avoid this CPU overhead while preserving the benefit of memory saving? To answer this question, we looked into the available hardware support. The recent Intel Xeon scalable processor introduced a coherent on-chip accelerator called Data Streaming Accelerator, or DSA, which can offload the operations like data comparison, CRC checksum calculation, and data movement. It also supports the access to host memory by virtual address, which simplifies the programming and the usage of DSA in the programming. And also it has the batch processing support. So naturally we can ask, can we use the DSA to help the memory deduplication? The answer is yes. In the previous slides, we break down the CPU cycles consumed by the KSM, and we can see that there are two most expensive operations, page comparison and checksum. And fortunately, they can be replaced by the DSA's data comparison and CRC checksum calculations directly. But DSA is not a drop-in solution here. First of all, this offloading opportunity is very promising because, as shown in this figure, we can see that DSA-based operations takes 6 times fewer CPU cycles than CPU-based one. But DSA is not a drop-in solution, and we will see why offloading alone is not enough. Okay, so first one, we implement DSA-ksm. It's a CPU DSA cooperative design for the KSM. It mainly have 5 steps. First, CPU prepares the work descriptor, which includes the address of pages and also the operations we want to offload. Second, host CPU submits work descriptor to DSA side. Upon receiving the descriptor, DSA reads the pages from host memory based on the address included in the work descriptor, executes the offloaded operations in the processing element, the PE here, and then finally, DSA returns the results back to CPU, for example, the compare result or checksum result to the CPU side. So DSA-ksm offloads the computation-intensive operations to the DSA side successfully, but we quickly find a bottleneck, which is the offloading latency. So let's see here. While DSA-ksm can save CPU cycles, this DSA-based operations suffers from the longer latency. So in this figure, we compare the latency of page comparison, mem-compare, and the checksum calculation here, when it runs on the CPU or when they are offloaded to DSA with various batch size 1, 2, 4, and 8. So let's say when the batch size is 1, meaning that we offload the operations one by one sequentially, the DSA-based operation present 2.6 times longer latency than the CPU-based one, which in turn leads to worse memory saving performance. And fortunately, the batch processing can elevate this long offloading latency by amortizing the submission and the waiting time overhead. For example, when batch size is equal or larger than 4, we can see the average latency per offloading here is similar or even less than the CPU-based one, which is a very good signal for us. So this finding motivates us to explore or use the batch processing of DSA. Unfortunately, KSM current design makes the batching difficult. Let me explain why. First of all, KSM maintains red-black trace to manage memory pages. And it only selects one candidate page to compare checklist and calculate checksum at one time. For example, here the candidate page is 66. So here I use a number to represent the page content for simplicity. And when we have one candidate page, then KSM will do a tree traversal by comparing the pages in the tree and with this candidate page. Let's say, for example, in this example, it will compare with 50 first, and then based on the results, it will go to right, compare with 67, and then finally compare with 54. And we can see here, these comparisons are ordered and sequential, meaning that you can only do the next comparison after you getting results from the previous one. So both single candidate page selection and ordered comparison hinder the batching processing with DSA for this comparison and checksum calculations here. So to solve these shortcomings, we propose Para-ksm, which transforms KSM into a parallelized way and enables efficient batch processing on DSA. Let's see how we do that. So in Para-ksm, we introduce two techniques. One is Para-ksm-C for the candidate page batching, and Para-ksm-T for the tree page batching. Let's go over them one by one. So as batch processing of checksum calculation on the candidate pages is very straightforward, here I will mainly explain how Para-ksm-C supports batch processing of comparison operations. In particular, I use unstable tree search and insertion as an example here. So in the tree search, Para-ksm-C aggregates candidate pages into batches and offload the operations by a single batch descriptor for this whole batch. And with this single batch descriptor, we can amortize the submission overhead and achieve lower average offloading latency. In this example, we have batch size to 3, and now instead of one candidate page, we have 3 candidate pages in a batch. They will be compared with, let's say, the first page, which is the root node 50 here. And in this batch descriptor, it includes the 3 work descriptor, and we only need to offload it by one time here. We only just submit one descriptor. After getting a result, which is on the right side, we can know that which page will be compared to each candidate page. And now we can construct next batch descriptor, and so on and so forth. We can get the last one until the bottom of the tree here. So as you can imagine here, we only need to submit batch descriptor for 3 times, BD0 to BD2, while in the previous DSA-ksm, we have to submit these work descriptors one by one, which means we have to do the offloading for 9 times. So in this way, we can save the offloading time and by reducing the batch descriptors, and thus we can achieve lower average offloading latency. However, the batch insertion into the red-black trees is not trivial. The reason is the red-black tree in the KSM are rebalanced after each insertion, and these insertions can change the comparison results for the other pages in the batch. So our solution is to track and update the predecessor and successor of these candidates. So the predecessor is defined as the largest page, which is smaller than the candidate page, while successor is the smallest one, which is larger than the candidate page. So let's look at this example here. So now I set the candidate page batch size to 5. And first, we will have, after the search on the DSA, we will get the search results, which include the candidate page and also their predecessor and successor. For example, for page 80 here, in the right tree, we can see that 67 is the smallest one, is the biggest one, which is smaller than 80. So we set the predecessor of 80 to 67, and similarly, we set successor to 92 here. However, the simple tracking is not enough, and we need to update it, and let's see why. So after we get these search results, Para-ksm-C groups the results based on their predecessor. For example, so for now, candidate page 70, 89, and 80, they will be grouped into the same group because they have the same predecessor, 67. And then we need to do the intra-group order and success update to guarantee that we will have the correct insertion order. Let me explain why here. So first of all, we formally prove that the inserting pages from different groups will not interfere with the insertion from other group. For example, if we insert page 20 into the tree first, and we can see that because 20 is not successor or predecessor of any pages in the group 2, so the insertion of 20 doesn't interfere with the insertion of the following pages. But for group 2 here, if we insert page 17, let's see, if we insert page 17 first, then if we want to insert page 89, its predecessor is 70. It's not 67 anymore. That's why we need to update them. And here we just update the successor. I mean, we can also update the predecessor. It's just a different way here. So here we update the successor to make sure that the insertion of previous page don't affect the correctness of the following page insertion. For example, if we insert page 89 first, we know that the successor of 80 should become 89 instead of 92 anymore. So in this way, we guarantee the correctness of the insertion within the batch. And the formal proof is available in our paper. So with this intra-group sorting and the success update, we ensure the correct insertion for all candidate pages. So this figure shows a step-by-step example. The blue arrow indicates the insertion spot for each page. Let's walk through the insertion of page 80 again as an example. So in step 4 here, we can see page 89 is inserted, and then between step 4 and step 5, we can see the tree is rebalanced. The page 89 is recolored and also it's promoted. So now we can still insert page 80 as the children of page 89 because we already updated its successor here. But you can imagine if we don't do that, we only know that the page 80 will be a children of page 92, which is incorrect. Another technique from Para-ksm is called Para-ksm-T, which is for the tree-page batching. So Para-ksm-T aims to batch the tree operations by speculatively compare its candidate page against all nodes within the M levels in the tree and submit the operations by one batch descriptor. And let's take this example here. We set M to 3, meaning that you will compare the pages. You will compare candidate pages with pages in the next 3 layers. That said, we need to offload 7 comparisons with one batch descriptor. But you can see that within these 7 comparisons, only 3 of them are in the search path, meaning that you waste more than 50% of DSA computing resources. This huge waste, and also it increases the memory bandwidth usage. Both of them block the deployment for the Para-ksm-T in the real environment. And as a result, our evaluation focuses on the Para-ksm-C technique. Yeah, here is a brief summary of our evaluation setup. We use 4th generation Intel Xeon scalable processor, which is equipped with a DSA, and this DSA has 4 process elements, and also we have Bluefield 3 for baseline. So first of all, let's look at the application performance. So here, what we care is the interference between KSM and the core application. We compare 4 cases here: CPU KSM, where KSM operations are running on CPU directly; DSA-ksm, we offload operations sequentially to the DSA; and stacks, which offload operations from CPU to SmartInc, but still it's in a sequential way, and also Para-ksm-C. And here we have 3 applications: liblinear, Graph 500, and Redis. So on average, we can see DSA-ksm, stacks, and Para-ksm-C can reduce the performance degradation by 2.5 times, 2.4 times, and 1.6 times respectively compared to CPU KSM, meaning that with this offloading, we can elevate the interference between core application and KSM successfully. And we can see here, Para-ksm-C has a slightly higher performance degradation compared to the DSA-ksm. The reason is, In the Para-ksm, we do some extra overhead. For example, we manage the successor, and also we do the intra-group page comparison here. Now let's have a look on the deduplication effectiveness, which is also the memory savings. And we can see here, Para-ksm achieves comparable memory saving compared to the CPU-based one, but for the DSA-ksm and stacks, their memory saving performance is pretty poor because they are long offloading latency. Even more importantly, we evaluated the deduplication efficiency, which is measured as memory savings per 1,000 CPU cycles. And here we can see Para-ksm is, so in this figure, these values are normalized to the CPU KSM case. And here we can see that for Para-ksm, it can improve the efficiency by 30 to 50% across all the workloads. So to wrap up, Para-ksm transforms the current memory deduplication mechanism from a sequential way to a more parallelized version. Together with DSA-based offloading, Para-ksm succeeds to offload operations more efficiently. And specifically, Para-ksm can decrease the performance degradation, achieves comparable memory saving performance, and also increase the memory deduplication efficiency. Overall, Para-ksm is a very practical hardware-software co-design that makes memory deduplication faster and more scalable. And thanks for your attention, and happy to take any questions.